Hello everyone. In this video, let us discuss about the derivation of capacitance between two radial planes in cylindrical system, taking the example of solution to Laplace equation for one-dimensional potential function. Let us consider two radial planes in cylindrical system. Now let us consider one radial plane at an angle of 0, this azimuth angle of 0, and another radial plane at an azimuth angle of 5. And when we consider the two plates are separated by at least an infinitely small gap, then there will be difference in potential between the two plates. And if the region between the two plates is filled with the dielectric material epsilon r, then we can estimate what is the capacitive effect between these two radial plates. The most important thing to note here is there should be at least an infinitely small gap between the two plates, because if the two plates touch each other, then there will not be any difference in potential between the two plates. We know conductor surface is equipotential. If two conducting surfaces touch each other, all will be at the same potential and there will not be any difference in potential between the two plates. To maintain the difference in potential between the two plates, there should be infinitely small gap between the two radial plates. We are considering the two radial planes are separated through a small gap, and the radius of the plane starts from rho naught and extends to rho 1. For both the plates, we can consider the radius starts from rho naught to rho 1. And let us consider the height of the two planes is L. So we can consider in z-axis from 0 to L is the extension of the plates, where one plate is fixed at an angle of phi, which is phi 1, another plate is fixed at an angle of phi, which is phi 2. As a special case, here we are considering the phi 1 is 0 and phi 2 is alpha. Here, we should also note that the angle phi should be represented in radians when we solve for the potential, which is a function of angle phi, where that angle phi should be indicated in radians. Now, in this case, if the region between the two plates is separated by an insulating material whose dielectric constant is given as epsilon r, then we can estimate the potential function between the two plates as a function of a single dimension, which is angle phi. And since the region between the two plates is free of charges, we can apply Laplace equation to find the potential function. And also between the two plates, what is the electric field can be found by taking negative gradient of the potential function, which we have found by solving the Laplace equation. We can also estimate the electric flux density as epsilon times E vector. Also, we can find the charge by using Gauss law from the flux density. And capacitance between the two plates can be estimated as the ratio of charge stored in either of the plates to the potential difference between the plates. Now let us consider the specific case where the first plate is connected to the negative of the supply voltage, which is also grounded, and the second plate is connected to the positive of the supply voltage, whose supply voltage is V0. We also have considered there is an infinitely small gap between the two plates, which makes the radius having the lower limit rho naught and upper limit rho 1, and the height of the plates is L, with the lower limit of z is 0 and upper limit of z is L. And we are considering the special case. The first plate is at an angle of 0 radian, and the second plate is at an angle of alpha radians. We also must know that this potential is a function of angle phi, where the phi should be indicated in radian values. In cylindrical system, we have to write the Laplace equation. We can write the Laplace equation and solve for the potential function. For that, we need to know the two boundary conditions. We can write the boundary conditions from the supply connection, where the plate at phi equal to 0 angle is at potential of 0, and the plate at angle phi equal to alpha is at a potential of plus V0. These two boundary conditions will be used to solve for the Laplace equation to get the potential function of angle phi, which is in radians. So we'll now write del square V in cylindrical system. This is the expression for del square V in cylindrical system, which is equal to 0, talks about the Laplace equation. And we also know between these two radial planes, the potential is a function of only variable phi. Thereby, differentiation with respect to rho will be 0 and differentiation with respect to z will be 0. Only the differentiation of potential function with respect to phi, which is the second order differentiation, this term only will be non-zero. So we can assume the first and the third term is becoming 0. Only second term is left, that is 1 by rho square dou square v by dou phi square is 0. Since it is a function of only phi, this partial differentiation can be written as the ordinary differential equation, which is the second order differential equation. Now we can rearrange these terms. This 1 by rho square can be brought to right hand side. This rho square in the denominator will be multiplied with 0 in the right hand side, which will make d square v by d phi square equals to 0. Now this is a second order differentiation of v with respect to phi. We have to do integration twice with respect to variable phi to get the potential function. First time integration with respect to phi will remove one differentiation term. So we will have only dv by d phi, and the right hand side integration of 0 with respect to phi will be 0. For the limits, we have no limits given. So we will be adding the integration constant C1. Now this has to be one more time integrated with respect to phi to get the potential function. So one more integration with respect to phi will remove the differentiation d by d phi, which will give v. And this integration of C1 d phi will be C1 into phi plus integration constant C2. Thereby, this is the function v, which is a function of phi, which is in radians, where this function should be given with the angle phi in radians. This is required when we solve numerical problems. This function takes the angle phi in radians only. Now we will be considering this potential function with constant C1 and C2. By applying the two boundary conditions for our special case, we will get the constant C1 and C2. Applying the first boundary condition, we will get V is 0 at angle phi 0, thereby 0 equals to C1 into 0 plus C2 and gives C2 as 0. Now by applying the second boundary condition, at angle phi, which is alpha, V is V0. So V0 equals to C1 alpha plus C2. We already know C2 is 0. Thereby C1 becomes V0 by alpha. Now by substituting C1 and C2 in the expression for V, we will get V, which is a function of phi, as V0 by alpha into phi. Now from this expression, we can estimate electric field intensity vector E, which is negative gradient of potential. This is the negative gradient of potential in cylindrical system. We have here B, which is a function of only phi. Thereby, differentiation with respect to rho and differentiation with respect to z are 0. Only this differentiation is left, which will give 1 by rho minus 1 by rho is there. Differentiation of this with respect to phi will be V0 by alpha into A phi cap. So this will be the electric field intensity vector, which has the unit volt per meter. Now from this electric field intensity vector, we can estimate the electric flux density, which is epsilon naught epsilon r times E vector. So multiplying this with epsilon naught epsilon r, we will get D vector, which has the unit coulomb per meter square. Next, we have to estimate the charge. From Gauss law, we can surface integration of D will give the charge by Gauss law. Now take this D and perform surface integration. We should consider the surface of this radial plane, where the surface of the radial plane has radius starting from rho naught to rho 1 and height starting from 0 to L. So we can take the limits for rho and z, and the integration is with respect to rho and z with the direction as phi direction. So ds vector in phi direction we should write with the limits of rho and z has to be taken accordingly. Now d vector, this d vector dot product with ds vector, we should do multiplying this phi direction component and this phi direction component. We have to perform integration for rho and z with this limits as per the dimensions of the radial plane. That is going to give the charge enclosed. So we can multiply this d vector and ds vector. Taking the dot product, you'll get epsilon naught epsilon r v naught by rho alpha into d rho dz. Now constants can be taken outside. Here the variable of integration is rho and z. So other than rho and z, we can take the constants outside. So epsilon naught epsilon r v naught by alpha are constants, and integration is 1 by rho d rho. This 1 by rho is there. 1 by rho d rho dz is there. Now 1 by rho d rho has to be integrated, and the limits should be from rho naught to rho 1, and dz has to be integrated, whose limits will be 0 to L. So this integration has to be performed. I'll write here and show minus epsilon naught epsilon r v naught by alpha. Now integration of 1 by rho d rho will be natural logarithm of rho, whose lower limit is rho naught, upper limit is rho 1, and integration dz will give z, whose lower limit is 0, upper limit is L. So this can be rewritten as logarithm rho1 minus logarithm rho naught into L minus 0, which is L. And this also can be written as minus epsilon naught v naught by alpha logarithm rho1 by rho naught into L. Now this is going to be the charge on the plates of this specific capacitance expression. So now we can write charge Q as minus epsilon naught v naught by alpha logarithm rho1 by rho naught into L. This is the charge stored in either of the plates of the radial planes, which has the unit coulomb. Now, one plate, if it is charged to negative charge, and the other will be charged to equal and opposite charge. Magnitude is going to be same. So in any one of the plate, how much of charge is enclosed, that will be the numerator for the capacitance calculation. And denominator of this capacitance is difference in potential between the two plates. By definition, capacitance is defined as the ratio of charge stored in either of the plates to the difference in potential between the two plates. Now, when we consider one is at the potential 0, another is at a positive V naught, thereby difference in potential will be V naught minus 0, which is V naught. So the denominator is V naught and the numerator is magnitude of this, which will cancel this V naught, which is going to give the expression for capacitance between the two radial planes in cylindrical system as epsilon naught epsilon r into the length of the capacitor L into logarithm of rho1 by rho naught, where rho1 is the largest value of the radius of this plane and rho naught is the smallest value of the radius of this plane, divided by alpha, where alpha is the angle of the second one. For this special case, the angular difference between the two is alpha. Here alpha is coming. Initial one is at 0 angle and the final one is at alpha angle. Thereby it is giving the angle alpha. For different boundary conditions, means for different angles, the expression will change. For this specific case of phi 0 at voltage 0 and phi alpha at voltage V naught, this is the expression for capacitance. For different conditions of phi 1 and phi 2, the different derivation is going to yield the different expression accordingly. I hope you have understood this. Thanks for watching the video.